deliver it live. So this is the chapter 7 and lecture 5. That means lecture 5 means topic 5. Okay. Although it is more, it is like third, how many weeks? It is now 4th week. So 3 weeks have completed, 9, and then this is actually the 11th lecture. But by the lecture here, I mean is the topic 5. Okay. And we are into the week 4. The And this topic is about the roots of the polynomials, which is chapter 7 of the textbook. Um, so in this topic, we will find the roots of the polynomial equations. So remember that from the last 2 chapters, we are finding the roots of the equations, basically non-linear equations. In the last 2 chapters, and then in the last 2 chapters, the methods which we have studied are applicable to all types of equations, bracketing methods and non-bracketing methods, and as well as the graphical methods. Polynomials are some special kinds of equations, okay? In which we don't have any other functions such as sine x, cosine x, okay, log x, exponential power of x, like that in those equations. And the same methods which we have discussed previously can also be used for their solution as well. But because these equations have a specific structure, like it has been shown over here, the roots of polynomial, the specific structure starting from the power of x equal to 0, that is, and then power of x equal to 1 to power of x 2, and then up to the last highest order power of x, which is n. So it is the nth degree polynomial, and each of these powers of x is being multiplied by the constant values a0, a1, a2, an. So these constants are they can be real numbers, or they can be even complex numbers as well. But for more simple cases, we will only consider those constants as the real numbers. So this form of the equations is the polynomial form. Due to their specific form, these types of equations have some extra methods by which we can solve them. So in this chapter, we will learn about those special methods for solving the polynomial equations, for finding the roots of the polynomial equations. So the methods which we'll be studying over here in this topic are thus only applicable to the roots of the polynomial equations. So they cannot be applied to the other equations which are not the polynomials, such as those equations which involve the trigonometric functions, exponential functions, etc. Okay, so when we have the polynomial equation such as this, we can say about the polynomial equations is that so the number of roots of the polynomial equations are equal to the order of the polynomial equation. So for example, if this equation has the highest power of x as n, so this equation will have an order of n. So it will be the nth order polynomial equation. So if the nth or if n is equal to 3, that means the highest order is 3. So then there will be 3 roots of the equation. If the highest order is 4, there will be 4 roots, and for the simplest of the polynomial equation, like the quadratic equation, the order is 2, so there are 2 equations, two roots of the quadratic equations. So n is the order of the equation, n are the roots. Okay, and the types of roots can be either real or complex or both. Okay, so if, for example, if there are 3 roots, so all 3 roots can be real roots, or there will be one real root and 2 complex roots, because the complex roots always occur in pairs, the conjugate pairs. So they are normally in the form of a plus b iota and then a minus b iota. So that iota terms, okay, square root of 1 terms uh, appears in pairs. So lambda plus mu iota or lambda minus mu iota. So these conjugate pairs always occur. So for an order 3 equation, we can say, so for an order 3 polynomial equation, we can say that it will have either 3 real roots or 1 real root. Okay, and 1 real root and 2 complex roots. So which means that we can say that any third order polynomial equation will have at least 1 real root, for a fourth order polynomial equation, so it will have 4 roots. So it can have all 4 real roots, or it can have 2 real roots and 2 complex roots, or it may have like all 4 as the complex roots. So a fourth order polynomial equation will have like no real root, 2 real roots, or 4 real roots. Okay, they cannot have like odd number of real roots. Okay, so based on this concept, so depending on this, we have now several methods which are available. The conventional methods are like the bracketing methods and the open methods. Okay, so the efficacy of the bracketing and the open methods depends on whether the problem being solved involves complex roots. If only real roots exist, these methods could be used. Yeah. So now, since we are talking about the roots of the polynomial equations, we have seen in the previous methods, the bracketing methods and the open methods, that in those methods we have only found the real roots. Okay, so those methods can only provide us the real roots. They cannot provide us the complex roots of the equations. So if we also want the complex roots of the equations, then these 2 methods, bracketing methods and the open methods, will not work. Okay, so therefore we need some additional methods for the polynomial equations, which can also find the complex roots. So finding a good initial guesses complicates both the open and bracketing methods. So also the open methods could be susceptible to divergence. So we have seen these drawbacks of the of these conventional methods, the bracketing methods and the open methods was that. So in the bracketing methods, the requirement is that we have to bracket the solution. So sometimes finding the bracket of the solution where for one value, the value of the function is less than 0. For the other limit, the value of function should be greater than 0. That means the bracketing range may be sometimes difficult in the conventional methods. And also on the other hand, the main drawback for the open method was that they are susceptible to divergence. They can often not converge, they can diverge as well. So they can, so therefore the bracketing methods and the open methods may not provide a full level or range of solutions which we are looking for from these methods. So therefore, there are a few special methods, and out of these few special methods, two of those methods, the Muller's methods and the Bairstow's method, have been described in this chapter. So we will look first at the Muller's method. So this was some introduction about the polynomial equations. Do you have any question on this?
No.
All right, so let's move ahead to look at the Muller's method. Muller's method obtains a root estimate by projecting a parabola to the x-axis through three function values. So this is the basic idea of the Muller method. Okay, so this Muller method, we can compare it with the secant method. Okay, remember that secant method was one of the method in the open method, which we have just discussed. So in the secant method, if you remember, you take 2 points on the curve, okay, xl and x0 and xi1, and then we extrapolate those points to cross the x-axis by the straight line. So we use a straight line joining these 2 points on the curve, and where that straight line joins the x-axis, then that becomes our next root estimate. Okay, so we are using a straight line. So for a straight line, we need at least 2 points to define the straight line. We need the coordinates of at least 2 points. So these 2 points we already know, and based on these 2 points, we can find the equation of the straight line, which crosses the axis over here, and then gives us the root estimate for our next iteration. Okay, so this is the process in the secant method. So the same approach is applied in the Muller's method, which is shown in this figure B over here. So in this figure B, you can see that the approach is the same, but instead of a straight line, we are using a parabola curve. So a parabola, remember that if you have some courses on the elementary geometry, the parabolas are those curves which are polynomials of second degree. So for example, the quadratic equation ax square plus bx plus c, the graph of that equation, it will be is a parabola. Okay, ax square plus bx plus c. So second degree curve. Okay, for a second degree curve, we use a second degree curve. So but if you compare it with the straight line, we need 2 points on the straight line. But for a second degree for a second degree curve, so for example, such as in the case of the parabola, we need 3 points to define that curve, because in the second degree curves, if you say that ax square plus bx plus c, there are 3 unknown coefficients, a, b, and c. We need to determine those unknown coefficients, a, b, and c. So therefore, For three unknown coefficients, we need at least 3 points to define that parabola. So now in this case, the function is shown in this black with this black line, and the approximated solution is represented in the form of a parabola. But for that parabola, we need 3 points, not just 2 points. So what are those 3 points? These points are called as x0, x1, and x2. Okay, and then based from these 3 points, we will calculate, we will estimate the fourth point that we will call as x3. And that fourth point will be the improved estimate for the curve. So this process will be repeated until we will get a reasonable degree of estimate, and then we will get closer to and closer to the curve. Okay. So is the difference clear between the secant method and the Muller method?
Yes.
Yeah. So in the secant method, we use the straight line approximation. In the Muller method, we use the parabolic approximation. In the secant method, we need 2 points, and then if we find the third, then we estimate the third point. In the Muller method, we need 3 points, and then we estimate the fourth point. Okay, so this is the basic difference. So having said that, there is now some sort of formulation for the Muller method. So the general form of the equation is something like ax square plus bx plus c, okay, if the function is represented like this. But for simplification, if we replace the values of if you replace x by x minus 2, then we can write a modified form of the function like this: f2 of x is equal to a into x minus x2 square plus b into x minus x2 plus c. So this function is of the same form, is of the same general form, ax square plus bx plus c. Only difference is that we have replaced x with x minus 2. And why x minus 2? Why not x minus 1 or x minus 0, as in this case, for example, x0, x1, x2, which we choose x2 in this case because we want our next point, which we want to find, which is x3, to be as close as possible to x2. Okay, so if we will, for example, if we will chase x1, then maybe we want the point that will be closer to x1. But in this case, our solution is here, somewhere here, which is, and the closest point is to that is x2. So that's why we will choose x2 over here. Okay, and by some yeah, and the next step we will take is that because we see that these 3 points are on the function. So therefore, their coordinates are x0, fx0, x1, fx1, x2, fx, x3, fx2. Okay, so if we input these coordinates into this equation, that means in this equation, so we put, for example, we will replace x with x0. So what we will get is f of x0. Okay, we will replace x with x0, so it will be x has been replaced with x0. And then similarly in this next equation, x has been replaced with x1. And in the third equation, x has been replaced with x2. And then in the last equation, we will see that x2 minus x2 will cancel out. So fx3 will be simply equal to c. And then later on, these 3 equations can be solved for the 3 unknowns, a, b, and c. So we have these 3 equations and we have 3 unknowns, And now you can see that it is easier to solve for those A, B, and C. So since two of the terms in the third equation are 0, it can be immediately solved for C is equal to, for C is equal to fx 3. Okay, so it should be C is equal to fx 3. Fx, uh, sorry, it should be, yeah, yeah, I think there is a typing error over here. If it should be fx1 over here, because we have replaced x with x1, so I think it should be fx1. Okay, and here if instead of fx3 it should be fx2. Okay, so C is equal to fx2, and then the other two equations can be solved. So there is a bit of algebra involved over here, but after you will perform do that algebra, you will see that we can come up with these equations. We can come up with these equations. So H naught, H1, we will find delta naught, delta 1. These are some intermediate variables which we will calculate for the calculations. But in the end, what you need to remember is that we need to find the values of A, B, and C. Okay, so A will be equal to this equation, B is equal to this equation, and C will be equal to this equation. Okay, so once we have the values of A, B, and C, that means then you can calculate the values of the next approximation x3 by using this equation. Okay, by this equation, which comes from the quadratic equation. Okay, and then their error can be calculated as, because x3 is the latest value, previous approximate was x2, so that will be the approximate error, and then plus minus terms yields two roots. So the sign is chosen to agree with the B. So this will result in the largest denominator and will give roots estimate that is closest to x2. So that means here we can see that we have to find x3, but here we have two signs over here. In this case, the sign, whatever the sign which we will take over here, plus or minus, we will take in such a way that the denominator will be the largest one. When the denominator will be the largest one, what we will get, the value which we will get will be the one that will be the closest to x2. So we want to remain closer to x2, and then iteratively we can we want to refine the solution. Okay, so this we can see with the help of the example. So once x3 is determined, the process is repeated using the following guidelines. So if only real roots are being located, choose the two original points that are nearest the root near root estimate x3. And if both real and complex roots are estimated, employ a sequential approach, just like in the secant method. So x1, x2, and x3 to replace by x0, x1, and x3. So this can, I think, this process can be clear if we can perform with the help of one example. So in this example, as you can see that the polynomial equation is x cubed minus 13x minus 12. And we have 3 points, 4.5, 5.5, and 5. And corresponding to these points, we can calculate the function values. 20.625, that means if you put 4.5 into this equation, we get 20.625. And similarly for 5.5, we get this value. For the value of x is equal to 5, we get the value of function of x is equal to 48. And then we need to calculate h naught, which is the difference between x1 and x0. Okay. And then we calculate the h1, which is the difference between x2 and x1, sorry. And after calculating h0 and h1, then we can calculate delta naught, which is the difference between fx1 minus fx0. So fx1 we already calculated over here. It is 82. Fx naught is 26.625, and x1 minus x naught we have also calculated. Similarly, we can calculate delta 1 from this equation. Okay, so delta 1 has been calculated. So now we have all these values to calculate A, okay, B, and C. So with this now we can we have already calculated the value of A, B, and C. So 15, 62.5, and 48. So now we can use these values A, B, and C to determine the root of x3. So here we need to make one check, because in the solution we have b square minus 4ac function. So first of all, you will calculate this discriminant b square minus 4ac. It will be 31.54. So now this 31.54 will be added with b. So the value of b was 62.25, okay, and its absolute value will be found, and then it will be subtracted from b and its absolute value will be found. So whichever the value, if this if the absolute value of this will be greater than this difference absolute value, so then our conclusion is that in this equation, for example, for x3 in this equation, we will employ the positive sign for this square root term, okay, not the negative sign, because the negative sign in this case will give us this smaller denominator, okay. We want the denominator to be bigger, so that our approximated value should be closer to this x2, okay. That will give us more accurate and more converging results, okay. So that's why you have to be careful when choosing any of those values, or in other case you can calculate for both plus and minus, and whichever value of x3 will be closer to x2, you can choose that value. So this is up to your choice. Do you understand this point?
Yes.
Yeah. So what I am saying is that we can get two values of x3. So one will plus b square minus 4ac under root, and one will be minus b square over 4ac under root. So whichever value of the x3 will be closer to x2, that value should be chosen for our next approximation. Okay. So uh, here, then we have chosen the plus value over here. So in this case, then from the value of x2, which was 5, we have got the value of x3, which is 3.97. Okay, so based on this 3.97 and the previous value of x2, so 3.97 minus 5 divided by 3.97, we have found the approximate percentage error, which is 25.74%. Okay, which is 25.74%. Of course, this approximate error is high, so therefore we need to do some more iterations. So then how we will perform the next iteration, because these values, how we will perform the next iterations. So in this case, then we will shift the values of x. So previously, because for the calculation of this x3, we need x0, x1, and x2. Okay, so the previously in the previous iteration, in this iteration, whatever the value of x0 will now become the value of x1. Sorry, in the previous iteration, whatever the value of x1 will be, then that will become the value of x0. Okay, and then the value of x2 in the previous equation will now become the value of x1 in the current equation. And the calculated value over here, 3.97, x3 will now become the value x2 in the next iteration. So in the next iteration, we will use these three values, and then you will repeat the process. So by repeating such process, you will see that in the next iteration, the percentage error will be 0.61 only. and then the next it will be even less. And then very quickly you can see that the solution will converge. So this can also be done in the Excel form. I don't have now time to show all these steps, although I have developed this sheet over here. So you will first uh, uh, calculate all these values x naught, x1, x2, and then f naught, f1, f2, h naught, h1, delta 0, delta 1. Then you will calculate a, then b, then c, and then you will calculate the discriminant b square minus 4ac, and then you will apply the check. The check means whether we want to use for the plus or minus, and then from here we will calculate the value of x3, and then you will calculate the percentage approximate error. So in the first case it was 25.7, in the second case it was 0.6, and then it was reduced to 0.02, and then it reduced to even less. And in the second iteration, you can see that the value of x naught is the same as this, which was previously for x1. The value of x1 is same as which is previously for x2. And the value of x2 is same as which was calculated in the previous iteration. So in this way, the algorithm will work uh, in the Excel. So when you want to do in the Excel, you can write all the necessary equations in front of you, and then it is very easy to formulate these equations into the Excel and then calculate it. So I hope it is clear. Okay. All right. So that was the Muller method. So do you have any question about this?
No.